Okay, hi, my name is Gabel, and I'm a system architect at Wix. I'm coming to JLabs to give a talk about our microservice architecture. What's slightly unusual about it is that it's actually simpler than most, and I hope you'll enjoy it. Thank you.
Dzień dobry Państwu, witam na kolejnej IT Akademii JLabs. Jak wiadomo, są to cykliczne, raz w miesiącu wykłady na różne tematy. Dzisiaj mamy wyjątkowego gościa, bo jest to Gabel, który przyjechał na Geekona, i zgodził się gościnnie wystąpić u nas. Także zachęcam do prelekcji. Przy okazji zapraszam na naszą nową inicjatywę, czyli na blog jlabs.pl. Tam są najnowsze wpisy, co czwartek wpisy technologiczne.
Okay, thank you. So, hi. My name is Gabel. I work for an Israeli company called Wix. This angle is a bit unusual for me, but I'll try and deal with it. So, just to give you a bit of context, microservices are not a new thing, right? You've probably heard dozens of talks, and may have even given a few. It's a pretty well discussed subject for the last few years. My goal for this talk, the two differences I aim to have from many other microservice talks is I'm going to be brutally honest. So I'm going to try and explain what we did, why we did it, where it failed, where it succeeded, and be very, very honest about what worked and didn't. And also, the primary difference, I think, is that Wix is no longer a startup. We're not a small company, but we're not huge either. So we have 130 odd server developers, which makes us a good kind of mid-sized company. So on the spectrum from, old school kind of banking software to Netflix, there's a whole spectrum of solutions, that may or may not be appropriate. We tend to pick the simple solutions. So, contrast that with a lot of other microservices talks, you will find over and over again over the course of this talk that we ended up with very simple solutions. We oftentimes just didn't solve problems that you might have been told are critical to microservices. And in a way, it might make this more useful because a lot of the solutions that we picked are kind of more accessible, more straightforward, easier to migrate to from more traditional technologies. I hope it's going to be useful to you. One last thing before we get started. We're a pretty small group here. So, this is intended to be useful for you. If there's anything you want to ask, anything that's unclear, something you want to argue with, or if you just want to, boo me off stage, it's all good. If either shut it out or raise your hands if you're not comfortable with that, I'll just pause and you can ask your questions. Once again, this is supposed to be useful for you. If it's not useful for you, it's a waste of your time. Mine is less important in this case, but, just make sure you get your, the most value you can out of this. So stop me if you need to. In terms of what we're going to be covering, I don't know whether there's an animation here, but microservices. We're going to be talking a lot about topology and networking because these are kind of the two core technical issues that you need to tackle when you go the microservice route. And a tiny little bit about operations, but also, once again, we're probably going to have plenty of time for questions, so I can cover anything you like, from organizational structure to technical solutions to problems that we've had, future directions. It all works. Just let me know what you're interested in. And until you do, I'm just going to, go with the talk as designed. So we're going to be using this kind of conceptual diagram a lot because it's an artificial example, but it's kind of indicative. This might be an e-commerce system, and it might have 3 microservices. You have your store service, your checkout, and your cart service. I'm not going to be talking about any of these in detail because what they do doesn't matter. Microservices, like microservice architecture, has less to do with what your system does, what its business domain is, and more to do with how it's constructed and how the different pieces talk to one another. So, it's easier to think about a practical example, but I'm not actually going to be touching on e-commerce in this talk. It's just an example. And to start with, the first kind of big concern when you go to microservices, right? Okay, maybe I should backtrack. Is anyone here completely unfamiliar with the topic? Like, is this microservice thing just brand new to someone and you have no idea what I'm talking about? Okay, well, it's 2017, so fortunately I don't have to redo the basics over and over again. Right. What I mean by topology is when you have this conceptual system and you have your various services and your various data stores, you also need to make a determination about which services reside on which host. Like how do you place your components on top of your physical infrastructure? How do you divide up your services, etc.? So the shape of like the physical layout of your logical system on top of your physical hardware is what I mean when I say topology, which really boils down to these three things. You have your service catalog, which is the list of things in your system. So it might be, those 3 microservices we gave as an example, or it might be anything else. You have your server inventory, which tells you, which servers you have, where they reside, what their capabilities are, how many CPUs, how much memory, etc. And then you have a mapping of service to host. And all of these things put together are your system's topology. Formally, we call the process of deciding where to place our services scheduling. Which brings us to the first major topic, service scheduling. Now, this turns out to be a fairly hard problem in practice, depending on your skill. It might be pretty simple, and it might be really, really hard, because you need to take a lot of different kind of dimensions into account. The first dimension is obviously resource utilization, which is the demand a particular service places on your physical infrastructure. Right? If you have your store service and its associated data store, it might need this many CPUs, that much memory, this many IOPS per second. There's always some resources that are required by any particular service. The other side of the coin, resource availability. So you have your actual physical servers, whether they're yours or hosted by Amazon, cloud-based or not, it doesn't matter. You have a set of available resources to play around with. Then you need to take into account things like failover, right? If you have a service, and for any kind of modern web-oriented system, you can't really have one instance of a service. You always have to have 2, if only for availability purposes. So failover is also a thing you need to take into account, because if you have 2 instances of a service and you place them on the same server and that server catches fire, then your system is dead, right? So that is also a concern you need to take into account. And then you have all these other kind of constraints. If you're an e-commerce system, you might, have to store credit card information, in which case you're subject to regulation. You're subject to PCI compliance, which means that you need to zone off a bunch of servers that are your PCI zone, that are dedicated to credit card information and have particular access privileges, and there's audit considerations. So anything, like any service that has to do with dealing with credit cards has to be in that zone, and this is something also your service scheduling needs to take into account. Now, I'm kind of overselling this in a way, because depending on the complexity of your system, this might be a no-brainer, right? If you have 5 services and 10 servers, you just take a piece of paper and you mark off the things that you want to put on each server, and you just divvy it up. It's an easy problem to solve. The problem only becomes difficult when you're dealing with much bigger, not necessarily massive complexity, but more complexity. When you have 10 services, or 100 servers, or 100 services, right? The complexity of just making these determinations, which services can reside with other services on the same server, starts to become a pretty tangibly hard problem. Also, if you're actually successful and you start scaling up and you add more and more services and more servers and more constraints, the problem just becomes, exponentially harder. So, how do you deal with that sort of problem? Well, you automate it. If you've listened to any of like the last few years worth of microservice talks, you will have heard of Kubernetes and Mesos and Marathon and Yarn and all these kind of newfangled technologies whose sole purpose is to solve this problem for you. Instead of having 10 servers and deciding which services to deploy in which server, you take those servers, you make them into a cluster, you install Kubernetes on it, and you let that, or rather, you let Marathon decide where to put your services. So that's, service scheduling in a nutshell is all about automation. And tools are getting kind of more and more sophisticated in making the determination of where to schedule your services. Everything works this way. If you run your services on Amazon, you have auto-scaling groups. That is also a form of automated service scheduling. So the first point I want to make, or rather the first example of this theme where if you can do something in a complicated way that solves a big problem, or a very stupid way that solves a big enough but smaller problem, we generally go with the simpler or stupid solution. So when it comes to server scheduling and automation, we don't really do any of that stuff, right? So this is kind of the first departure from your kind of run-of-the-mill Guild or Netflix microservice talk. We don't actually invest that much in automating our orchestration, automating our service scheduling. We started off with a very naive solution where we actually had just this static mapping of services to hosts that we managed manually. That worked quite well for a few years, but we eventually started to run into just scaling issues because it becomes harder and harder to manage a static topology the more servers and services you have. To give you an idea of scale, like I said, Wix is a good mid-sized company. When I first wrote this presentation, which was just under 2 years ago, we had a total of about 200 services, like different services in production, and they were using in total about 300 physical servers. Now we're at 500 microservices in production on top of between 500 and 1,000 servers. Okay, so the numbers have increased somewhat, and we still use the same infrastructure. So it actually scales nicely. Like if you're not going to be radically successful, or perhaps your system fundamentally requires a lot more scale and complexity than kind of traditional techniques solve, just go with the simple route. What we ended up with, what we're currently doing today, is we still do everything statically and ahead of time. Like our topology is basically defined in what you can think of as an Excel sheet that just maps services to hosts. It's not actually an Excel sheet, and it is partially automated in that if I, as a service owner, need a new instance or I'm adding a new service to the mix, we have a very, very simple UI that's tied to our topology servers. And it just basically gives us a good guess of where to place our services. If I need a new instance, we have our server inventory that's registered somewhere. The algorithm goes like this. For each server in server list, if server can satisfy the required resources, println server name. That's it. That's our algorithm, right? So we automate the simple task of looking for a server that is appropriate for that service. And everything else, like the optimizations, the zoning, figuring out if their services maybe are competing for the same resources and have to be split off into different services, we still do that manually. Our ops people just go on in, edit these tables, and that's our static topology. And it turns out that this is actually a pretty decent solution as long as your scale is kind of middle of the road. Once again, 500 services, 1,000 servers, this is still good enough, but we're starting to kind of come up against the scale limits of the solution. Yes? So I'll repeat the question for the camera. The question was whether or not this whole solution is homegrown. Yes, it kind of is. So I'll get into a bit more detail about kind of what our topology and deployment stacks look like, and there's, if it's unclear, then just ask later and I'll go into a bit more depth. So this is how you schedule services. Now, once you've scheduled your services, you have, once again, kind of the dual problem that you need to solve, which is, okay, we have these 3 services, and it's a graph, right? It's a dependency graph between services. And then when a service actually needs to actually issue a request against a dependency, you have this edge on the graph. The next question you need to figure out an answer for is, I have my topology in place. How do I actually find the service? There's a tendency to conflate the 2 concerns, which are service scheduling and service discovery. And it turns out that you don't really need to solve these 2 things at once. So your topology system can be thought of as a registry of services and servers and the mapping between them. Discovery is the mechanism you actually use for when you need to issue a request. I need to talk to this logical service, give me back an actual address that I need to send my packets to. So that's service discovery in a nutshell. And the way I personally like to think of it, it's a bit, I've not found any other kind of talk that makes this particular division, but I think it makes sense. I like to divide service discovery solutions into 2 axes: physical versus logical and static versus dynamic. Static versus dynamic is kind of obvious. Static means that everything is known ahead of time and there is no kind of runtime figuring out of where things are. Dynamic obviously means that you know very little ahead of time and you kind of figure things out at runtime as you go. By physical versus logical, I mean you can have a solution where your clients, the things that talk to your services actually know the full extent of where these services are. So for instance, if you have, take DNS for example, okay, the classic example, right? When you use DNS for service discovery, which is a very old school but kind of very tried and true technique for service discovery, one way to think about this is when you consume the service that is google.com, when you do a web search, right, you don't actually need to know where the servers are. The language that you use to talk to your discovery mechanism, which is DNS, is, I have this logical name called google.com. Give me a list of possible targets, a list of possible physical addresses that I need to then actually send the packets to. A different example for that would be configuration files, which is also a very tried and true and practical technique. If your configuration files for your services have things like URLs for target servers, usually the language that you use to say I need to talk to my dependency, which is say the e-commerce store service, I take that logical name, and from my configuration file, I actually get back a URL or a list of URLs to talk to. Whereas in the physical space, you actually don't have logical names. You deal with physical addresses. So I'll get back to this in a second. I'll give an example. So I like to divide the universe into these 4 quadrants. On the lower left are static and logical kind of service discovery mechanisms. DNS and configuration files are kind of the go-to solutions. Easy, well understood. They work if you're running at a reasonably small scale. That is a perfectly viable solution. On the right end of the spectrum, you would have your kind of the dynamic and logical solutions. So one of the more well-known solutions these days is Consul by HashiCorp, which, I don't know, how many people here have actually heard or used Consul, of Consul? Okay, so that's about a good third, maybe half of the audience. What Consul gives you is a distributed system where you can actually, services at runtime register to Consul. Like they say, okay, I'm a store service, I'm an instance, this is my IP, now I'm available. Console deals with kind of it's kind of a database of these services, and clients, when they actually need to talk to the store service, kind of like DNS, they actually go to console through one of several APIs. One of them is DNS, and they ask, okay, give me a target for this logical service that is the store service. The reason it's dynamic is because the topology is not known ahead of time. Right? The fact that services actually register themselves, instances register in console, they register themselves as available for handling that sort of traffic, means that nothing really is known ahead of time. Like if you start up console, it's going to start up with an empty topology, and until services actually register, then you can't actually provide a service to your customers, and that's why it's dynamic. Then on the top right quadrant, you have things like Eureka, which is the Netflix kind of service discovery solution. They're also dynamic, but they're physical in the sense that each client kind of has the knowledge of the entire topology. They don't just know the logical names; they also know like the layout of all of the servers in runtime. Also, lots of custom solutions kind of work this way. Between those kind of two right-hand quadrants, as long as you're kind of dynamic and you know what you're doing, it's more of an aesthetic preference. Like, which do you like best? Pick one. They're both going to work. The thing you don't want to do under any circumstances and at any scale is to be in the upper left quadrant. You do not want to do that. By which I mean a physical and static thing is service discovery mechanism is what we call a hosts file. If all of your hosts, all of your physical servers have a host file that contains your entire topology, then that is a physical topology, physical service discovery, as well as statically known ahead of time. And managing that is insane. It's just, why would you do that to yourselves? So just don't. Anything in the right-hand quadrant is modern and workable. Anything in the left-hand quadrant is antiquated. If you're on the top quadrant, you're screwed. If you're on the bottom quadrant, you're fine up until a certain scale. Like at some point, it just becomes hard to manage manually. Does this kind of make sense? Okay. The next question is obviously, okay, well, what do we do at Wix? What is, where are we? Well, as it stands currently, we're in the kind of lower left-hand quadrant. We have a, we have a topology service, if you will, a registry of services and servers, but it's not used at runtime. It's used for convenience. We manage our topology through an internal tool that we call Frying Pan. That is in answer to your earlier question. It's completely in-house. It's actually very, very simple. From that, we generate configuration files on deployment. Right, so it's still statically known topology ahead of time. It's still logical because it deals with mapping kind of service logical names to to URLs. We don't actually manage all of our hosts ahead of time, and we generate everything with Chef when we deploy. This has worked quite well for us. It has some limitations, which I'll explain in a bit. And this is why we're kind of headed in this direction. Now, I'm not sure that we're going to end up with a custom solution. This was true probably about a year ago. Things haven't really changed, but the people involved with this process have, and they might have different preferences. So we might end up with a console-based solution or smart stack or something like that. But we're definitely heading in the direction of a dynamically managed topology and service discovery. Sorry? Okay, not having not having worked with Smart Stack in production, I have no opinion on the matter. I like it philosophically, but I really don't know, so I'm definitely not gonna argue the point. Either way, we're kind of headed towards a more dynamic topology service, and the reason for that is that we've grown to the point where we want to be able to make topology changes on the fly. So having a static topology actually prevents you from making use of a lot of kind of the niceties of modern software development. If you're running in the cloud and you want to run, you want to use auto-scaling groups, you want to be elastic. Well, with a static topology, you're either completely not going to be able to do that, or you're going to be able to approximate a dynamic, like dynamically growing and shrinking topology, but with certain limitations. So for us, the limitations are that we generate all of this stuff through Chef, and we configure Chef to run once every 15 minutes just to check if there are any changes. Now, you can actually give it a good swift kick in the ass when you want it to run, when you have kind of a well-known trigger and you want it to regenerate your configuration files right now. But Chef was never designed for that sort of thing. It's not fast. It takes a while to run. Even the simplest Chef run on any of our servers will take upwards of 2 minutes just to get through everything and make sure nothing has changed. It was never designed for rapid changes. It's a provisioning tool. Provisioning is not something that happens on the fly all the time, right? So it's not a good solution for us, and it kind of prevents us from taking advantage of the fact that which is, by the way, an inevitable question. So before you ask it, we have both our own data centers and we use cloud providers. So we have services in our data center in Austin. We have a second. It's not exactly decommissioned, but we mostly use it for testing purposes in Amsterdam. And then we actually have all of our services also typically available on EC2 on Amazon, and some of our services on Google's cloud platform, whether on Google App Engine or the managed container infrastructure. So we kind of do everything. But because we share the same infrastructure between all of them, we can't actually take advantage of what Amazon brings to the table. We can't auto-scale because our topology is inherently static and our service discovery is inherently static. My machine just went crazy. Never mind. Seems to be working on screen. Okay, so as I mentioned, we have our internal tool called Frying Pan. We export, which we use to manage topology. We export it to Chef, or rather we integrate with Chef, and Chef actually generates configuration files on deployment. We do have a live registry of services that we keep in Zookeeper, but currently we only use that for deployment. Like our deployment toolchain uses that to maintain the state of deployments in the system. So it's not actually used for either topology management or service discovery. All of that stuff happens ahead of time. And that works, right? This is just one example of where you can, like, if I was redesigning Wix from the ground up today, I would not go this route. I would pick one of the kind of newer technologies, because if you're going to be building it from scratch, you might as well take advantage of like the latest and greatest off-the-shelf components. I would probably use like Console or something similar, because it's convenient, because why not? But if you're kind of migrating from an existing application and you're either kind of trying to break down a monolithic app into microservices, or even augment it with microservices, you don't have to go the full Monty. You don't necessarily need to go with dynamic topology or client-side load balancing, or all of these solutions that give you a lot of power, but also are rather complex and may solve problems you're just not very likely to have anytime soon. So, once again, an example of keeping it simple. Any questions before we move on? Cool. Networking, right? This is getting to the meat of things. Let's have another look at this diagram. We have our store service and our checkout service, and our store service actually depends on the checkout service, and it needs to ask it questions. So if we have these two services that are going to be talking to each other, and because we have a topology solution in place, we know how to place them on servers, and because we have service discovery in place, we know how one of them can find the other. Now the question is, how do they actually talk to each other? So this is known as a protocol. And when deciding on a protocol in your microservice architecture, there's kind of one or two major decisions that you need to make. The first is what style do you use? Do you use RPC style, which is kind of a natural fit for a lot of software systems? RPC style just basically means like, you know, remote. It literally means remote procedure call. It means that a service asks a question of another service, awaits the response. Request-response style. It's simple, it's point-to-point, it's like a well-understood thing. And then you have your other style, which is message passing. Your async, message broker, Kafka or RabbitMQ, whatever it is you feel like, based architecture, which requires a broker. Now, it turns out that whichever way you go, there's actually a bunch of things that you need to solve in any case that are not dissimilar between these two styles. You know, topology we've already discussed, but your kind of serialization protocol can be the exact same regardless of which style of service communication you pick. And there's operations around this. You need to monitor, you need to know the latencies, you need to know, the queue sizes. All these things generally are very similar whichever way you go. So at Wix, we actually, up until fairly recently, have only had, we kind of took the chicken shit way out, right? We did the simple thing that could work. We chose RPC style. We use HTTP. We use JSON over HTTP. Our JSON RPC is kind of an ad hoc custom thing that was put together, but it's pretty straightforward. It works. It's very solid. It's been serving us really well. Like we begun the process of breaking Wix apart into microservices around 2010. Our current kind of server infrastructure has been evolving since then, but has remained largely unchanged. Specifically, the RPC subsystem has remained almost without any changes since its inception, because it's not that big of a problem to solve. So it's rock solid. It's been working really well for us. It's a bit ugly because it's, it started off as a Java thing. Nowadays we work in Scala, so there's some limitations there. And it's synchronous or blocking or threaded, whatever you want to call it. This is kind of our canonical stack. We also have a fledgling message passing protocol that we call Greyhound. It obviously is a message passing protocol. It uses the same kind of custom JSON serialization and custom JSON schema that we use for our RPC subsystem. We use Kafka as not exactly a message broker, but because kind of the infrastructure that makes sure messages from one end get to the other, which is arguably a disservice to what Kafka can do, but is a pretty common use case for it. And then, in terms of what it gives us that RPC doesn't, well, it's async, which is, fundamentally a different thing. Like, there are certain things you cannot do with a strictly synchronous or blocking style API. This is async. It's replayable because it's based on Kafka. You can always kind of go back in time and replay messages that you've already consumed. It's kind of still experimental. Like, we're using it in production, but it's only been gaining traction recently, and we're still kind of figuring out what the APIs should be like, how to monitor that sort of thing. It's still in progress. So really, most of our server-to-server communication is RPC style. And, that's good enough, generally. Like, it solves most problems. Once you have a protocol in place, the next problem you need to solve is one of my favorite problems. It's called load balancing. And load balancing kind of comes in two major flavors. You have your traditional centralized load balancing, by which I mean you have a server that depends on you have a service that depends on a second service. That second service has a pool of instances of servers available for its use. And then you have in the middle some sort of load balancer. It might be F5, it might be Nginx, it might be Varnish, depending on your architecture and your context. in either case, what it means is that you actually have a centralized component in charge of balancing the load. There's quite a few advantages to that. It's very, very, very simple. It's simple to set up. It's simple to reason about. It's simple to debug. Like, you can't really get that much wrong with it. But it's limited. It's limited in scale. I will admit that the likelihood of your own servers in Java or Python or Ruby actually saturating Nginx to be remote, like, you're not really going to be running into scale issues unless you're working at extreme scales. But it is limited in flexibility. So certain types of decision making or routing that you might wish to do, you can't really do with off-the-shelf components. Once again, probably not a problem or a limitation you will ever run into in any kind of production system. Not because we're so cool, or it's more like because Netflix are so cool, right? And you don't get that many companies working at that scale of complexity, working with call graphs that are that deep. You just generally don't get that level of complexity in any production system. So the limitations are actually not really a big concern usually. One huge advantage of centralized load balancing is that it's simple and the clients don't need to know shit. They just need to know the HTTP URL to talk to, and that's it. It's that simple. Like, you don't really need a client per se. You need an HTTP client, which is something, assuming of course you're HTTP based, which is something that's available in any language and any platform. Like, you don't have to worry about it. And you don't have to share client code between your services. And it's very suitable for static topologies, not so much for dynamic ones. Because if you're changing your topology on the fly, if you have like auto scaling in place or something, then you need to actually update the central load balancer with the new topology. That is, it doesn't really lend well to a dynamic topology. But once again, old school, simple, works, battle tested, and probably will solve your problem. On the other end of the spectrum, you have your Twitters and your Netflixes and your, kind of newfangled microservice style companies that prefer a distributed mode of load balancing. And by that I mean there is no Nginx. Every client, and by client I mean if service A depends on service B, then service A is a client of service B. So every single client needs to handle its own load balancing demands. Which means that every service has an implementation of a load balancing client that deals with talking to the topology service and making decisions as to where to send traffic. Now, there are advantages to this. To begin with, it's inherently more scalable. Like, if you don't have a single kind of point of contact, a bottleneck or a single point of failure, if you will, then inherently you can reach higher scale. Probably not a thing that will be of any concern to you. For us, we're nowhere near maxing out what Nginx can do for us in terms of scale. So probably not like a really tangible benefit. It is, though, very, very, very flexible. You can do, like, if you've heard all of these wonderful talks about circuit breaking and all of these, circuit breaking, load shedding, how to manage retries, exponential backoff, all of these cute techniques, you can theoretically implement them on top of Nginx, but no one does that because why? So a lot of these techniques are applicable when you choose distributed load balancing, but it has the big disadvantage that it's a thick client. Like, if you put all of your load balancing logic on your client, then you need to actually implement that load balancing logic. And then if you, say, want to have an alternative tech stack, you want to be able to write your servers in Python as well as Scala and Ruby and whatnot and Node.js, then you will need to re-implement this not inconsiderable amount of logic for every implementation of your architecture, which can be very expensive. Surprisingly, there's actually a third option. This is what's kind of really, really easy to miss. I have not used it in production, so I can't say if it's really as good a solution as it sounds. I like to call it quasi-distributed. So Smart Stack, for which we have a very strong negative testimonial right here in the audience, does something that at least conceptually is very smart. What it does is it runs a process on each of your hosts, and that process is basically the load balancer. It's basically in charge of taking in traffic coming from services on that particular host, and it decouples the concern of actually implementing client-side load balancing into a separate process. So it keeps your services simple, but it still gives you a lot of the flexibility of kind of your big Netflix-style distributed load balancing solution. So that might actually give you the best of both worlds. Once again, I've never actually, I like it philosophically. I've never actually used one of these solutions, so I can't attest to how good they work. Console can be, but not really, for subtle reasons that we can talk about that later. It might have changed, but from what I know, you can't actually make it work like this. We do centralized load balancing. We use Nginx. Right? Nginx is our load balancer of choice. We don't actually have that many instances, and they serve all of our external and internal traffic. Easy. We already had a static topology system in place. We already had Chef in place. All we needed to do is render the correct format of configuration files for Nginx and just let it rip. So it's dead simple, and it really has been working well for us. This is not our major concern. So yeah, keep it simple. It's going to work for you. Any questions before I move on to the next point? Which is, I'm not going to tell you. First, I'm going to explain this title. There is a thing in any microservice architecture that people don't like to talk about. And that thing is called IDL. And by IDL, I mean Interface Description Language. There's always some form of IDL in any microservice, like any microservice architecture. And by IDL, I don't mean any specific format or protocol for describing interfaces, but you always need to describe your interfaces somehow. Because if you don't, you're not going to have any clients, and your clients are not going to be able to talk to you. So, obviously there's something that explains how to consume your services to prospective clients, even if they're in the next room over. There's a number of ways to do this. You could go the informal route. So a lot of certainly in the earlier stages of development, you can solve a lot of these problems with things like README files or code samples. That is often kind of enough when you're getting started. Like, okay, my service exposes this at this URL, it exposes these endpoints. Here are sample inputs and outputs. These are the headers you need to send. You can document that pretty simply, and it scales not very well. But I mean, if you have a small number of services or a small number of people actually involved in consuming and producing these services, that's good enough. Then you have your formal techniques. So you might use Swagger for documenting kind of your REST APIs. Protocol buffers and Thrift and Avro have kind of built-in IDL solutions. Certainly Protobuf and Thrift do. And if you're still kind of stuck about 15 years ago and you just can't shake off this horrible thing called .NET Web Services, you might end up using something called WSDL or WSDL for describing your services. If anyone here uses SOAP, I feel your pain, and I'm sorry for you. So it's still essentially a form of IDL. It's just a shitty one. So don't use it if you can avoid it. So you have these, or you can have an ad hoc solution like us. For us, we have a public interface site member service that has a method called getMembersById, returns a site member's DTO, blah, 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 blah. This is Java. So we actually use Java interfaces to describe our microservices. This is our IDL. This might seem horrible, and in a way it is, but there's kind of very good reasons why we ended up this way. First, to give you a bit of context, Java interfaces actually lend really, really well to this particular type of problem. I'm not advocating that that's what you do. Let me right off the bat say you should not be doing this. But if you think about how these things were designed, and once again, this is a solution that's been in place since about 2010, maybe 2011. So it's not new by any means. When it was originally designed, we were a JVM shop. Our code base at that point was mostly Java. Nowadays, fortunately, it's mostly Scala and not Java, but beside the point. Java interfaces actually lend really, really well to RPC-style service description, right? What is an RPC service? It's essentially an interface exposing a bunch of endpoints, or methods, if you will, that take in arguments and have an output. That is essentially Java interfaces, right? It's very, very convenient. So if you don't mind being very strongly coupled to like the Java ecosystem and the JVM, that is actually a really sensible solution. Now, nowadays, you have better solutions, because 6 years ago, protocol buffers were definitely a thing within Google. Thrift wasn't even on the radar. Protocol buffers were in use within Google, but it wasn't like a mature, well-understood solution in the open source community. So you didn't really have kind of a go-to solution for IDL. Back then, WSDL was still a thing, and we would not want to ever use that. So it actually made sense at the time. Where this kind of breaks is that, like I mentioned, we use JSON for our kind of for serializing and deserializing our data between our RPC subsystems. Now, that in of itself is fine. JSON is a perfectly sensible format for data transfer, unlike XML, which was originally designed to solve that problem and failed miserably. JSON is simple enough that it makes sense and it works. The problem is, how many of you are in the Java space? Java, Scala, any JVM language? Oh wow, that's actually a bigger majority than I expected. Okay, I'm going to take a guess. Don't even bother raising your hands, but I'm going to take a guess that everyone who's raised their hands deals with JSON in one form or another, and they use a wonderful, wonderful library called Jackson. Because Jackson is the de facto JSON library for Java. You might be using something else, but that's kind of the exception to the rule that proves the rule. The problem with this is that Jackson is a runtime reflection based library. And what this means is that in order to actually determine how Java objects get serialized or deserialized to JSON back and forth, the way you kind of give hints to Jackson as to what the shape of the JSON is going to be like is through annotations. This is okay. I mean, it's a little bit ugly. I have a personal aversion to anything that deals with runtime reflection. I really, really hate reflection-based mechanisms for a number of reasons that have nothing to do with microservices. Where this really, really hurts us, and that's something I'm going to get back to, is that it's almost impossible to just look at a class definition along with its annotations and derive from that what the end result, like what the JSON result of serializing an instance of that class will look like. It's almost impossible to do that because not only does it depend on a lot of factors like which annotations are present and custom serializers and deserializers, which you can't reason about externally. Also, it depends on the runtime state of the library itself. Because if you're using Jackson, as most of us do, you don't use Jackson as is. You need to register modules for dealing with things like Joda time or Java time or various collection libraries that you end up using. So actually, the resulting JSON depends not only on the class definition and its annotations, but also on the configuration of the object mapper that you use to write, to actually emit that JSON. So it's almost impossible to figure it out ahead of time, and that means, once again, we're very tightly coupled to the JVM, and this really gives us a huge headache if we want to kind of expand to other tech stacks that are not Java-based. I'm going to circle back to this point in a bit. The gist of what our tech stack looks like on the server side, we use Jetty. We use it in an embedded fashion. We don't use it as an app server, but we use it basically for dealing with HTTP traffic, HTTP routing, all of that, like basically as to provide us with the servlet API. On top of that, we use Spring MVC for historical and unfortunate, but mostly for historical reasons. And using Spring MVC obviously means that our services are, our servers are mostly built on top of Spring. We have some custom handling, lots of custom logic, but it doesn't matter. Fundamentally, we're a threaded server running on top of the servlet API with Spring and Spring MVC. That is our tech stack. And once again, it's been like fundamentally unchanged for the last 5 years. We have kind of packaged it differently over the years. So we've moved from using Jetty as an actual app container to using it in an embedded way. We package kind of our internal tools around Spring and Spring MVC into two different kind of ways to consume our infrastructure. One is the old one, it's called Wix Framework. The new one is called Wix Bootstrap. These are implementation details. Fundamentally, our tech stack is as old school Java, like you wouldn't be surprised to run into that sort of tech stack 5 or 10 years ago, right? Not that much has changed. You will notice that because we use Jetty, we're also blocking and threaded. And some of you might have panicked a little bit at seeing this because async event-driven servers are kind of all the rage in the last couple of years, and I'm not saying that's a bad thing. I'm saying that's not always the necessary thing. I'm going to circle back to that as well. In terms of what our RPC clients kind of look like, so on the JVM, it's also built on Spring. We use proxy classes that we generate at runtime. So I mentioned before, we use actual interfaces as our IDL. So when, as a client, I want to actually use a remote service via RPC, I just get in an instance of that interface from Spring. Behind the scenes, it generates a proxy class that goes to our RPC subsystem, but to a client, it just looks like a Java interface. While that has advantages in terms of it's fairly convenient, philosophically, I think that sucks because it doesn't give you a very clear distinction of, you know, if I'm using two interfaces, is one kind of in process, is one, you know, is the other actually going over the network? I don't like that there's no explicit distinction between an RPC call and an in-process method call. I think RPC fundamentally is kind of a busted model, but we need to put things into perspective. This has been running Wix successfully for about 6 years. So not to toot our own horn, Wix is a pretty successful company. You know, since this infrastructure was put in place, we've grown probably at least tenfold in terms of people, if not more than that. We've IPO'd, we've increased our market. Like where it counts, this has served us really, really well. It works. It works fine. We don't have any forest fires that we need to put out on a daily basis. Like nothing is on fire. This whole thing works really well for us. It's just that aesthetically I don't like it. We do have an alternative stack based on Node.js. There's two issues when it comes to re-implementing our tech stack on top of Node.js, and I'm not even going to go into whether or not I like Node.js because that's completely irrelevant. What is important is this is kind of a proof of concept that we can actually do polyglot development in our like server group and actually build servers on a completely alternative non-JVM based tech stack. And there's two problems we needed to solve. We needed to find a way to actually produce RPC clients and servers. And as it turns out, converting Java interfaces into kind of whatever, into client libraries on top of Node.js, dealing with the interfaces is really easy. Dealing with the IDL is actually really easy. Where it screws us over is in this last bullet, which is manually converted entity schema. Because, as I mentioned before, we use Jackson, and Jackson is impossible to reason about in a static way. It's impossible to know, just looking at a class, what the resulting JSON is going to be like, what are the edge cases for that resulting JSON. Don't even get me started about things like polymorphism, etc. It's a bit of a mess, which means that we can't automate any of that. Converting a Java interface into a client library is as easy as, writing another client generator for Thrift. It's trivial. Converting the entity schemas, like the parameters and the return values that our RPC services actually use, turns out to be almost impossible to do. So we don't automate this. We do this manually for every platform, for every consumed service. This might be trivial, and in many cases it is. Sometimes it gets a bit hairy if you're dealing with a particularly weird kind of data model. Generally, it's not a huge concern from the point of view of a person actually consuming a Java service from Node.js. But from an organizational perspective, now that we have somewhere around 500 microservices, this becomes a huge issue with recurring cost. Having to, for every tech stack, for every kind of published service, manually produce a JavaScript representation and serialization, deserialization for every kind of data object that crosses the wire is incredibly costly. It's just painful. And this is one result of a very, unfortunately, not forward-facing decision made very early on in the process. So if there's one lesson you can learn from this is pay attention to your schema mechanism and don't ad hoc ones. Nowadays you can use JSON-LD. To hell with it. If you're desperate, use XML schema. I don't care. Just use some well-understood portable schema model. Don't use ad hoc solutions, because this is the sort of thing that will really screw you over in the long run. Does that make sense? Are you scared enough of doing ad hoc schema management now? Good. Mission accomplished. Any questions so far? Once again, if you have any questions at any point, just, you can shout it out. Sorry? So, repeating for the camera, are we planning on switching from this to a more kind of modern, off-the-shelf solution? The answer is, in the general, yes. We're heavily looking into gRPC. But either case, we're going to be stuck with this for a while. Even if tomorrow we add gRPC to our, as an alternative solution, and everyone is super happy with it, we're still going to be stuck with 500 services built on top of this. So yes, we are heavily investigating. We're looking concurrently at using Thrift and Thrift for solving this particular problem, and gRPC is kind of a wholesale replacement for our communication, like RPC style communication. It's very likely to happen because there's just no reason to keep doing the thing that we know isn't a good idea. But it's gonna take a while, and even when it does, we're still gonna be stuck with legacy services for a number of years. Okay, a word on cascade failures. I have mentioned that we use Jetty. It's threaded. It's blocking. If you've heard any, one or two at least kind of modern microservice talks, especially the ones dealing with asynchronicity in microservice architectures, and that you should always be using an event-driven server, and blah, 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 blah. The reason is usually this, around cascade failures, because, fundamentally, is there anyone here who doesn't know what I mean when I say cascade failure? Should I explain it? Okay, cool. So a cascade failure is generally a category of issues that can happen in your system where having a dependency break can bring down the thing that depends on it, the things that depend on that, and it just cascades through your system and brings the whole system down. So a canonical example for this would be on a threaded server model. if you have a threaded server and it has like a JDBC connection pool. Once again, I'm using Java terminology, but essentially it's the same regardless of language or infrastructure. If you have, say, 50 threads available for dealing with requests, and your database barfs, but it breaks. But it breaks in a way that doesn't just give you a no to any request, but instead it times out on every request. And you're not careful, it's very easy to get to a point where the threads that actually take in user requests then issue a request to the database, get blocked on that, time out on the database. In the meantime, your customers that depend on you actually time out in their request against your server. And the more this happens, the less threads you have for actually taking in, threads available for taking in further requests. Now, this is not a cascade failure. The cascade failure happens when, as with any system, what you see is intermittent failures, and you say, okay, well, it's every now and then it's possible that I might time out against the database because it's, you know, it might be busy replicating, or I might have a network hiccup. Let's add retries. And then your dependency starts retrying against you, against your service. Your service is already blocked and can't deal with any requests because the database can't deal with any requests. So your the thing that depends on you keeps retrying, exacerbating the problem on your end, and also the threads dealing with user requests on that particular server also get hung up waiting for you to time out, and that can cascade up the stack, further and further up the stack until the point where your system basically can no longer handle traffic. That is an issue particularly with threaded servers, because if you're going to be blocking, then you need to be very careful not to run out of available request threads, and you also need to be sure to manage your timeouts in a way that doesn't allow the failure to cascade up the call graph. There are ways of dealing with this. First of all, a lot of the problem goes away if you use an event-driven server, because then you don't block. Right? You have a callback, and that callback may be abandoned because it's timed out, but you're not losing system resources on that timed out request, on that inherently failing requests. Then you have kind of mitigation strategies that you may have heard of, bulkheading, circuit breaking, load shedding. I'm not going to get into bulkheading and circuit breaking because those are pretty well understood patterns, but also a little bit out of context. Load shedding, by the way, is something you should definitely be doing. Load shedding basically means my service knows how much capacity it can handle. If more requests come in than I'm able to handle, I'm just going to refuse them. Okay, so load shedding in the world of web and HTTP basically means responding to a request with 503, I think, service unavailable. 503, right? He's ignoring me. Beautiful. Sorry, what's that? Okay. If I remember correctly, it's 503 service unavailable. That is a signal that your server sends to its client that says, look, I have not dealt with your request. I cannot deal with it right now at all. You're free to retry it at some point in the future. Right? It's not that the request had failed. It's that the request was never even attempted. I did not serve this request. Other ways of load shedding for a TCP load balancer might be dropping packets. It's fine. Basically, don't deal with more kind of inbound traffic than your capacity allows. Just drop it on the floor. If you can, send a signal up the stack that you can't handle the load. If you can't, just drop it on the floor. At least don't break. Right? Because if you try to tackle more load than your capacity, what usually happens is that you end up breaking. Like you end up with like infinite garbage collection, or your service times are going to be so high that it's not going to be worthwhile to anyone. Other than load shedding, we don't actually use any of these techniques. We don't have circuit breakers. We don't have bulkheading. We are a threaded server-based company, which begs the question, how do we deal with cascade failures? So when a cascade failure actually happens in our infrastructure, the thing that we do is we cascade fail. We might die. It's possible that a failure deep within our architecture somewhere might hypothetically bring down our whole system. And I can tell you that it has happened, but it's actually not as big a problem as you might think. So I remember when kind of circuit breakers kind of became an interesting pattern. That was probably about 5 years ago with what's called Deploy It, I think. That's the book that kind of made it mainstream. Everyone was talking about circuit breaking. Everyone was talking about moving off of threaded servers. Everyone was talking about how you have to implement these things or your system will fail. And the reason why everyone was talking about it is the only two companies to actually seriously invest in microservices at that time were Netflix and Twitter, and they were the only ones talking about it. And at their scale, you actually do have to deal with these problems. At Wix scale, at our current scale, it turns out that this is very, very, very rare. So we're not actually that worried about the fact that our servers are threaded. We do worry about load shedding because that solves a whole bunch of other problems. Like we throttle requests. If requests come in at a higher rate, we just refuse to accept these requests, refuse to serve them. But that does not necessarily have to do with cascade failures. That is just good engineering practices. So it's not as big a concern as you might think. If you're designing a brand new system, sure. Take the best of breed architecture, best of breed off-the-shelf infrastructure that you can find, have it deal with these problems for you. If you're migrating off of a traditional or monolithic system, you don't necessarily have to solve these problems ahead of time. It's going to be a long while before they come back to bite you in the ass. Yes? Okay, so for a bit of context, the reason he knows what the hell he's talking about is this is Avishai. He's a colleague of mine from Israel. But that's just beside the point. Like, if anyone is interested in these techniques and whether or not we approximate or apply them, feel free to ask. But generally speaking, we don't really, at least not intentionally. So, to summarize the bulk of this talk, does it go? Does it work? The short answer is yes. These numbers are not up to date, but this infrastructure has been organically evolving for the last 6 years. There's been, fundamentally, there hasn't been that much that has changed in our microservice architecture over the last 5 or 6 years. There's been a lot of people that have worked on it and made incremental improvements to kind of our server framework. The number here says that we're running 200 services in production. It turns out that the number nowadays is closer to 500. And it's known quantity, right? We know our architecture inside and out. We know its limitations. We know how to operate it. We know how to scale it. We know where it breaks. We know where it's not likely to break. It's a battle-tested, well-understood architecture for us. So the reason why we're not ahead of the curve in terms of switching to an event-driven model with client-side load balancing, dynamic topology, all of these nice things that are kind of sold as intrinsic to microservices in the modern world is because effectively, there's two reasons. The first is because we've been evolving our infrastructure, and any one of these things is a very radical shift from our established and entrenched architecture and practices, but also because we don't necessarily understand how to properly implement these things in many cases, because you need to invest the time and effort. You need to actually run these systems in production, see where they break, figure them out, get up in the middle of the night, solve a bug, and hope never to run into it again. You need to do that for a while before you can call your architecture stable. And we haven't had a compelling reason to break out of the established mold that we know how to operate and are very happy with into something that gives us a kind of hypothetical advantage but we're not comfortable operating in production at our scale. That being said, so it served us really well, but it has some inherent limitations, and we're starting to kind of strain the limitations of this particular architecture. So if you're kind of wondering, okay, well, you know, this is a pretty straightforward and pretty simple, at least I hope I got the message across, that this is pretty straightforward and pretty simple. Where it breaks, like the kind of scale that you need to look out for and start paying attention to if you're going to go this route. If you've grown to the point where you want to do polyglot development, if you want to work in multiple languages, especially ones that are not available on the JVM, being coupled to the JVM becomes a huge issue. And that's the problem that we have today. We have a very much a custom JVM-based stack. It's very expensive to port. So our kind of Node.js-based solution actually took a lot of effort to put together, and despite the fact that it doesn't solve all of the kind of interoperability problems, you know, like you actually have to manually convert the schema if you're building a client that consumes a Java service from Node.js, it was still quite a massive effort. So that is kind of a concern. I'm not going to go into this in any amount of detail because I don't want to waste your time. What you need to take into, like, what you need to learn from this slide, without going into too much detail, do not use thread locals. If you use thread locals for whatever reason in your server, you are going to be screwed, like we are screwed. So just don't use them. Okay. Once again, without going into too many details. A very quick word about operations, and then we'll wrap it up. You know, we have our servers, our services. The next question is, you know, what's up? Are they alive? Are they healthy? Are they happy? Our monitoring kind of system, or our kind of operational stack, is actually a lot more primitive than you'd think. For host monitoring, so because we're not strictly cloud-based, we actually need to monitor physical servers, like in the old school Linux sysadmin way. Use Sensu. We used to use Nagios. We use Sensu. It kind of monitors the usual stuff like host CPU utilization and disk space and all that stuff. There's nothing fancy here. We use Pingdom for actually quite a little. We don't do very much kind of end-to-end testing as part of our monitoring suite, but when we do, we use Pingdom for that. And we have a custom BI toolchain that I'm not going to go into any detail on because that's a whole nother talk. When it comes to actual monitoring of the system, really there's only three things you ever give a damn about with production systems, production microservice-based systems. You care about logs. We don't log. Isn't that lovely? Like, we basically use SLF4j and logback, but that's wired nowhere. We don't have any central log aggregation. We don't use Logstash or Elk, or like, we don't use any of these things. We basically don't log. Instead, as we've kind of learned, we pay more and more attention to metrics, to application metrics, to infrastructure metrics, that sort of thing. We use Dropwizard metrics, which used to be known as CodaHell metrics, as the library that gives us a convenient interface for emitting metrics. I have my issues with it, but it does work. We use Graphite, same as most everyone. We use actually Grafana as kind of our dashboarding system, and Graphite is our backing data store. We also use a SaaS metric platform called Anodot, which gives you a lot of what Graphite offers, but also does anomaly detection of dubious value. We have a lot of custom code in our infrastructure to kind of emit standardized metrics across all of our services. So for instance, the RPC client might emit latency metrics. The RPC server might emit failure rates. We have a lot of these kind of custom metrics that we emit out of our infrastructure, and actually I think that is probably the single most powerful tool we have for telemetry, for debugging and monitoring our system. But it's pretty straightforward. We use Anodot and we use New Relic extensively, which is unfortunate, by the way. I don't think New Relic is a worthwhile investment if you're going the microservice route. There's a lot of argument around that, not just, yeah, sorry? APM. I don't think that is a worthwhile investment personally, but a lot of our server devs seem quite happy with it. So, you know, it's definitely an easy way to get started with kind of a turnkey, mostly reliable monitoring solution. And we manage alerts via PagerDuty. Yeah, like I said, no logging, not any logging to speak of. I've yet to run into, like, as far as I'm concerned, like in my experience, organizations that actually heavily invest in logging, both in infrastructure and like their log messages, the quality of their logging infrastructure and their log messages are unicorns. It's so rare to actually find a solid, workable logging solution in place in a microservice-based infrastructure. I imagine that it happens, but I've yet to experience it in person. I've never seen, like, never actually worked for or with an organization that had any kind of common sense in how they handle logging. So we kind of took the opposite route and said, well, we know that we're not going to be able to make sense of our logs, so let's pretend they don't exist. And we don't generally use logs for production debugging. Obviously, we use feature toggles and kind of A/B testing extensively. We have an open source experimentation framework, or A/B testing, if you will, framework called P-Tree, which you're welcome to look up. We use it very heavily, both for kind of dark launching products, or for A/B testing, you know, different re-implementations of the same thing. We use it for everything, basically. And ideally, as with any microservice architecture, you would want distributed tracing, which is basically a mechanism that allows you to either in aggregate or for a particular request actually get kind of a call graph. Like if you've ever opened Chrome's developer tools and actually saw, like, it gives you a timeline of all the resources loaded on a page, you kind of want that same visualization for your microservice-based system, because it gives you a good idea of like where the hotspots are, where you need to debug, where you need to invest in performance improvements. Unfortunately, we don't really have that. So I would have loved to have had it, but we have like two separate kind of experimental extensions to our architecture to enable this, but it's not mature or production grade enough that I would actually call it useful yet, at least not in the broad sense. So in terms of the important stuff, like this is kind of a very broad overview of how to get from the concept of having a microservice-based architecture to hearing all of the cool shit that Netflix and the big boys out there are doing and the way that they think about these things, and then getting back to real life and figuring out that a lot of that stuff is either impossible to implement given our legacy code base, or just too expensive to implement, or of dubious value, or just too complex for most of our pre-existing engineers to handle. All of these things are fair assessments. Like admitting that you're going to have a very hard time getting your existing engineers to actually deal with these kind of new paradigms and new systems, like it's the grown-up thing to do. If you have that problem, and when you have to kind of retrain 100 engineers, you might have that problem, then it's something you need to take into account. Or if you have a lot of legacy code that you're going to need to interoperate with, and it just turns out that it's too hard to do that with like an event-driven re-architecture or whatever, then maybe you don't have to. You can keep it simple. You can solve your problems iteratively. You can choose the older well understood solutions, sometimes it makes sense to do that over kind of newer solutions that give you more power but are more difficult to grok. Just take it easy, right? Look at what you're trying to accomplish, and if possible, if it's a greenfield project, sure, pick the latest and greatest. You're not going to regret it. If you're going to build your new microservice infrastructure on top of Finagle or Hystrix, and you're going to use their fault injection framework and all of that stuff, you're going to reap the benefits of a lot of hard work by very, very crazy smart people at these companies that have solved the problems for you. But if you're starting off with a pre-existing system and you're trying to figure out a sensible migration path away from your older kind of monolithic app, you don't necessarily have to solve these problems. A lot of these problems are problems you will never have because you're not likely to be at the scale where they become an issue. Okay, Wix currently is a roughly $3 billion company, and we run 500 services on top of what is essentially a 6 or 7 year old infrastructure that doesn't do anything dynamically, that is threaded and blocking, that doesn't do circuit breaking and deals with cascade failures. We use MySQL, old school, ugly MySQL, and we use it very happily because it works and it gets us there. So don't be afraid of picking the simple solution. Just do what makes sense for your own organization, and don't be blinded by problems that Netflix has, because they're very likely not to be your own. And if there are no more questions, there are questions. Cool. Yes. How many people do we have to manage? You mean how many developers we have that are dedicated to the infrastructure, to like maintaining this? Not as many as you think. We basically have 3 infrastructure teams that deal with various aspects of it. I would say probably about 10 people in total. Like, it depends on which aspect, because I'm not counting, for instance, operations engineers that deal with like the deployment system and the provisioning system. So it really depends on which part of it. In total, our server group is about probably about 130 engineers in total. So, even if you add like the ops guys to that and subtract from that people who are not directly working on this tech stack, that's the amount of people that we have. So we have about 10% of our workforce kind of dedicated to infrastructure. That is the rough percentage.
Do you have a clear division between developers and ops?
So the question is, do we have a clear division between developers and ops? The answer is, we have that clear division. I'm not sure that I philosophically agree with it, but the way we're currently structured is that our ops team is basically an infrastructure team. So they're in charge of, they own Frying Pan, which is the kind of in-house topology tool chain. They own the deployment stack. They own the provisioning stack. So that would be Chef and all of its kind of associated stuff. But they don't, and the networking, routing, like externalized HTTP stuff is also part of that team. But if a service breaks, unless it brings down Wix in an all hands on board kind of way, generally they're not involved. So I don't know that the distinction is entirely healthy, but it makes more sense than many other organizations I've spoken to about this.
Based on what you already said, I think that you are, as a company, more use a full system. It doesn't mean, doesn't matter if it's VM or Perpetual, but it's a full system, not a container.
So I managed to, up until now, avoid the D word, which is the word that ends with ocker. So we're investigating containerization, but to my knowledge, We have very, very few kind of experimental services that run containerized.
You mentioned previously that you are using container managed services on.
Yeah, well, from the point of view of our infrastructure or deployment stack, etc., we don't care. Like, it doesn't really matter if it's bare bones, VM, or containerized.
You're using, you're running chef clients inside containers?
Don't think so, but I couldn't describe what we do instead because I don't know I don't know that, shall we say, experiment that well. I don't know the details. Go for it.
If you actually is fine time basically runs chef. The chef deploys a bunch of services from a specific Replica. Those services are deployed on the operating system. It's not a container. It's a full-blown operating system, either VM or physical host. And when it deploys a service could be a number of things. It could be a Java, it could be an old school WoW file. And it can also be some kind of process, usually Docker. So we do actually have services running in Docker, but the machine itself is not containerized in any way. Okay, physical or virtual machine.
Okay. Next one. How do you deal with state of the services? I mean, each service has its own state, or they are shared state?
So I suppose it depends on what you mean by state. One of our, it's not even a guiding principle. It's one of those unwritten rules where if you do anything else, we're gonna kill you. Is you do not share databases between services. So every microservice, if it needs persistence, has its own data store. And if you, like a team, like a product domain, with a single team that owns a bunch of services can make the determination that for their own reasons they want to share a data store, a database, Elasticsearch, whatever, between their own services. But even that is severely discouraged. Actually, I don't think I can, off the top of my head, name a single service that does that. Although we probably have one or two of these unicorns. We do have guidelines for like service authors about do's and don'ts. So from strictly not even an architectural standpoint, from just keeping like your boundaries between your services sane, do not ever share data stores between services. If you have two services talking to the same MySQL server, you are screwed. And if you're not screwed now, you're going to be screwed in a month or in a year. Don't do that.
Next one. How do you do performance analytics around the whole stack?
How do you do performance analysis around the whole stack? Well, we don't do performance analysis per se, but whether from our various performance metrics or through New Relic's less reliable reporting of latency metrics, we have a good idea of, like, if you monitor the response times of your kind of external HTTP, like HTTP services, like at the top of your call graph, you have your service that takes in a user request and then it fans out in your system and you monitor that, then you know how long it takes. Now, if that meets your SLA, you don't really need to dig any deeper. As for what we do when it doesn't meet SLA, we don't actually have that much kind of codified methodology or codified tool chains to help us do performance analysis. Generally, it's in an ad hoc basis, but I mean, there aren't that many tools and techniques you can use at any given resolution. There's only so many ways to measure a thing. So when we have that problem, we usually just put together like a task force or whatever it takes of, you know, a number of smart people and have them tackle that particular problem. But we don't have any kind of organizationally mandated tools or methodologies to deal with performance.
Could you briefly describe how Kafka behaves in your environment? I mean, from my own personal experience, Kafka is only good with growing stack prices. So how much time was invested in Kafka work?
So that is like Greyhound, which is our message passing protocol built on top of Kafka. One of the reasons it was designed, and I don't necessarily agree with that decision, but one of the reasons was to kind of abstract away the hairy details of dealing with operating Kafka in production away from people who just want to message pass shit between services. As far as I know, it's been working pretty well for us, but it's worth noting that we don't currently put any, like we put production load, we use Kafka in production, but we don't have any significant scale of load that we put on it. So, you know, how easy it is to push Kafka out of its comfort zone and into breaking mode, I don't know, because we just don't use it that heavily at the moment. That will probably change in the fairly near future because we're putting more and more stuff on it, but I don't have a good answer to that question. So before that, anyone else? Because I don't mind like the stream of questions. I just want to make sure everyone gets their chance. Okay, so I think probably last one because I think people are getting drowsy.
Just out of curiosity, which distribution are you using?
Which Linux distribution? We use a bunch of them because it depends on whether you're talking, like we use Debian for our co-located services and I think also our EC2 instances. Google, obviously, like if you run on their managed containers, like whatever, they're going to do whatever they feel like. And I think we also have an experimental Ubuntu-based, yeah. But from my point of view, it's one of those who cares kind of things. Like the people who care are the people in charge of doing the provisioning, the server provisioning. But from an organizational API standpoint, if you will, like if I'm consuming the service that is give me a provisioned server, I don't really care as long as it's POSIX and it works. Yeah, but if you're interested in the details, I can put you in touch with Dimitri, who's like the head of our ops team in charge of like the provisioning infrastructure, and he'll probably talk your head off about the various disadvantages each and every single Linux distribution has. Okay, I think that's a wrap. If there's any questions, please feel free to continue afterwards. And thank you very much for your time. I hope this was useful to you. Have a terrific week. And for those of you going to GeekCon, see you there. Thank you.